I'm a second year medical student. Okay, I'm gonna repeat. Okay, good evening, everyone. My name is Ayat. I'm a second year medical student, and today we'll be covering MOL 10, metabolic effects of insulin and glucagon. All right, so we'll be going over the role of insulin and glucagon in energy metabolism, then the anabolic effects of insulin and the catabolic effects of glucagon, then the molecular mechanisms, basically the physiology of insulin and glucagon, and then the counterregulatory hormones, basically the hormones that go against some of the main hormones that we're going to be talking about. Okay, so first of all, there is an overview. Uh, so depending upon the level of nutrients in the body, depending upon if we're eating food or fasting, there are two different hormones that act. So say if our nutrients they increase, if our nutrients increase and we're taking in food, our insulin increases. Why? Because when we take in food, our blood glucose increases and our insulin increases to decrease the blood glucose. So it's basically for storage or anabolism. And say if our nutrients decrease or we're fasting, our glucagon increases so that our glucose increases because we have no other source of glucose. So it causes breakdown or catabolism. Catabolism basically is like cut, same thing. So catabolism, it cuts down the sources of glucose to give us glucose. Now there's four different organs or tissues. There is the liver, the adipose tissue, the muscle, and the brain. These are the four main organs that are used in basically the insulin and glucagon fluctuation or sort. So basically, the insulin and glucagon are the main hormones that act according to the availability of the substrates, which are basically the nutrients. Then you have the nervous system. The nervous system basically acts on the adrenal gland and releases catecholamines. Catecholamines include your epinephrine or norepinephrine, which are basically the fight or flight hormones, which you use in times of stress or like emergency situations. So this is an overview, and we're going to be going over everything again. Okay, so you have the biosynthesis of insulin. When insulin is first synthesized from the insulin gene itself, from after transcription and translation, you have this signal peptide. The signal peptide, the only job of signal peptide is to tell the whole structure to go into the ER. When it goes into the ER, it gets rid of the signal peptide. So you remove the signal peptide. After removing the signal peptide, this is called as a proinsulin. So it goes from a pre-proinsulin to a proinsulin. Then from the proinsulin, it's going to go into the Golgi apparatus, where it's going to be cleaved again, and then it forms our main two products, insulin and C-peptide. All right, so this is basically whatever I just said. So if you want to read it, it's in the written form. Um, so insulin basically has a half-life of 6 minutes, and that's very, very short compared to the C-peptide, as you can see. Its half-life is greater than insulin, and it's a marker of insulin synthesis and secretion. We're going to go over that next. First of all, because insulin has a shorter half-life, this duration allows it to make rapid changes in the body. So, for example, if your blood glucose increases, all of a sudden it can rapidly act and decrease it, and then it rapidly degrades. Degrades. Why does it rapidly degrade? Because if you have insulin in your body for a longer amount of time, your blood glucose is going to keep decreasing, and then you're going to end up in a state of hypoglycemia, and you do not want that. All right, that's our insulin. What's C-peptide? So C-peptide is basically something that's formed after the cleavage of proinsulin, as I said before, and it's only formed through endogenous insulin. So it can only be produced in your body. So for example, in some patients like diabetic patients, you give them exogenous insulin to help with their diabetes. That does not have C-peptide. So this is how you measure like the original level of insulin. Also, because insulin has a shorter half-life than the C-peptide itself, you cannot directly measure the insulin. So we measure the C-peptide instead, right? In the structure of insulin, I don't think it's that important in MOL, maybe in ERP because you're taking the same thing in ERP. So structure of insulin, it's a peptide chain, it's an amino acid chain. It has 51 amino acids. This slide is basically just memorization. There's two polypeptide chains. There's A chain and there's the B chain. The A chain is shorter. It has 21 amino acids. B chain has 30 amino acids. Okay, so this part is the confusing one. because the doctor herself got confused in this in the recording. So there is intermolecular. Inter means between two different chains, and there is intramolecular. Intra would be on the same chain itself. So there is two intermolecular disulfide bridges. You see, there's two sulfides. These are disulfide bridges between the two chains. So inter, and there is one intramolecular disulfide bridge within the A chain itself. Okay, so that's basically the structure of insulin. Now coming to where insulin is produced from, it's produced by the beta cells of islets of Langerhans of pancreas. So these are the pancreas, and there's a cell here which is called the beta cell. There's the alpha cell which produces glucagon, which we'll be going over later. Um, so the most important part of insulin is coordinating the use of all the fuels. Fuels as in everything you gain from nutrients. For example, the glucose, the fatty acids, the amino acids. Its main function is anabolic, so it has the synthesis of. Okay, so you have glucose, and you're gonna take all the glucose, and you're gonna keep storing it, right? And all of that together is gonna form glycogen. Then you have all the fatty acids, which together form triglycerols or TAGs, and then you have amino acids, which come together to form proteins. So the basic function, what you have to know from insulin, is that it's anabolic, and the fact that I'm sorry, one second. It's anabolic, and it has uh, it synthesizes the oh my God, sorry. It synthesizes the production of things. It's basically used in storage. All right. Um, okay, this is basically the recap of what we just did. The fact that over here you can see that inside the nucleus you have the gene. It's getting transcribed and translated, and then you have the pre-proinsulin, which is then cleaved in the ER, and then you have the proinsulin, and then the proinsulin is cleaved again in the Golgi apparatus to form the insulin and the C peptide and the insulin, and this is then gone into the secretory granules. When it goes into the secretory granules, it's released through exocytosis, and that whole process has a different physiology in itself, which we'll be going over later again. All right. Uh, Okay, yeah, so that's basically, and then she gives you this diagram, which is pretty easy. It basically just says if you have increased amino acids and fatty acids, you have a positive effect on insulin. Why? Because again, amino acids, it's like you have amino acids, and then you have one protein. So you're like taking this and forming one clump, so it's easier to store, kind of. You know what I mean? So you're basically taking everything and storing it. Amino acids into proteins, glucose into glycogen. We'll talk about epinephrine later. So all of this basically stimulates insulin, and then yeah, you have more release of insulin. Okay, how is insulin secreted? Um, Okay, so first of all, you have glucose, right? You take in a meal, and then the meal eventually you digest the meal, and then you have glucose. Now, this glucose comes near the pancreatic beta cells, which are very sensitive, and they go inside by a glucose transporter, specifically the GLUT2 transporter. And as they go in, they are catalyzed by something called the hexokinase 4 or glucokinase enzyme. When they're catalyzed by the glucokinase, they're phosphorylated and trapped inside the cell. So now they cannot go out anymore because they're phosphorylated into G6P or glucose 6 phosphate. All right. After this happens, the glucose 6 phosphate undergoes glycolysis. Then it goes through the Krebs cycle or the citric acid cycle, and then through the electron transport chain. And then this is the whole process of basically forming the ATP, and this keeps happening and happening, and you have increased ATP. Eventually all of this ATP, it goes and it blocks the potassium channels, the ATP gated potassium channels. When it blocks the potassium channels, the potassium cannot go out, so the positive charge inside the cell increases. When the positive charge inside increases, you have depolarization of the cell. Eventually the depolarization causes the voltage gated calcium channels to open. So now calcium helps release the insulin granules from through exocytosis. All right. Okay. Flashback. So you took this in MOL 1, and you took this in enzymology. enzyme in one of the enzyme lectures, so I don't think I have to go over this as much, hopefully. Um, so you have glucokinase and you have hexokinase. The thing with glucokinase and hexokinase is that they're basically the same thing. You have glucose over here, you have glucose come in, and the glucose turns into glucose 6 phosphate. So both of them essentially have the same function. So what's different about them is that glucokinase is present mostly in the liver and the pancreatic cells, and hexokinase is present in basically everywhere else. Right? Now glucokinase has lower affinity. Lower affinity means that it's not easily like, say for instance, it's not easily attracted to things. So you need a lot of effort for this dude, right? You need a lot of effort. You need a lot of substrate. So you need a lot of glucose for it to be like, okay, now my time's come. I'm gonna start releasing a lot of insulin. Okay, so it has a lower affinity, a high Km. This is what confuses people, so don't get confused. Lower affinity, high Km. You need high efforts, right? And it has a high Vmax. So when it has a lot of glucose and it goes like, all right, now my time's come, it's gonna react really fast. So it has a high Vmax. Unlike hexokinase, present in the other cells which has a lower Km. So if it has a low glucose level, it's just gonna start working and has a low Vmax and it's gonna work at a low pace. Again, glucokinase is not feedback inhibited. I think you took this too, but I'll just re-explain it. So as I said, that hexokinase is going to be present in all the other cells. All right. So for example, it's present in your muscle cells. So this hexokinase is going to start converting your glucose to G6P, and eventually, like, it's going to serve as a source of energy for the muscle itself. So when the muscle has enough source of energy, it's going to stop the hexokinase from functioning. Because why? Because it has enough energy already, right? It does not need more energy. It's going to unnecessarily deplete its sources if it just keeps making more energy. So then it's going to stop the hexokinase, and that's feedback inhibited. In glucokinase, what happens is glucokinase is in the liver and pancreas mostly, and basically, when the glucose comes in, it goes into the liver and pancreas, and it just keeps making insulin. So there is no way that you could just take the insulin and go back and stop the glucose, because you're consuming food and you're making the glucose. So there is no way in between that the insulin would go and then it will go and feedback inhibit it. So it only happens in hexokinase. That is why she says that glucokinase is not feedback inhibited, unlike hexokinase. All right. Ingestion of a carbohydrate meal leads to a rise in blood glucose. Basically, consuming nutrients leads to increase in blood glucose, and the beta cells are the most important glucose sensing cells. This is basically like a summary again. They have the GLUT2 transporters, and then you have the glucose converting to G6P through the help of glucokinase. And then at blood glucose levels above 45. So 45 is basically give and take the normal ones. So above 45, glucokinase phosphorylates glucose. Why? Because at above 45, again, blood glucose increases, so glucokinase has to act and phosphorylate glucose in amounts proportional to the glucose concentration. Basically, the more glucose you have, the more it's going to phosphorylate. That's basically what it means. Okay, so there's these drugs that have a similar mechanism of action. They're anti-diabetics given to diabetic patients. They're called sulfonylureas. Okay, okay, so they're basically oral agents. My bad, guys. I have a pro asketamol. Sulfonylureas, they're anti-diabetics and they're oral agents. All right. What they do is they work just like the ATP thing. They come here. Wait. All right, over here. They come just like ATP, and they close the ATP gated potassium channels. When they close that, you have increase in calcium. Calcium goes, releases insulin. So their main function, because of this, would basically be to release insulin. So it helps diabetic patients release more insulin. It's used in type 2 diabetes, because your um, in type 1 diabetes, I don't know if you guys took this yet. Um, so in type 1 diabetes is basically like an autoimmune condition, and in this, the cells of the pancreas are destroyed itself. So the medicine cannot really do shit there. Oh, okay. You can't really do stuff there because the cells are destroyed anyways, right? You can't really do anything. But it's used in type 2 diabetes because your cells are still surviving, so you can still produce the insulin. All right. Then you have the gastrointestinal peptide hormones, or the incretin hormones. Okay, these include the glucagon-like protein 1, GLP-1, and gastric inhibitory polypeptide, GIP, and they release from the small intestine after food intake. So as in when you consume food, the small intestine releases GLP-1 and GIP. Now what they do is they go to the beta cells and they increase the sensitivity even more to glucose, which causes even more rise in insulin. Now there's something called the incretin effect, which means that oral glucose induces a larger secretion of insulin than IV. Why does this happen? Because it's if you take oral glucose, it's going to be like you consumed food, right? You basically just consumed food, and then the small intestine is going to release these GLP-1 and GIP-1s, and that is going to increase the sensitivity. So now, if it increases the sensitivity, it's going to give you a rise in insulin. So that's why oral glucose induces a larger secretion of insulin than IV does. All right, when is insulin inhibited? Insulin is basically an anabolic hormone. So if you consume glucose, if you consume amino acids, it's going to take all of that and it's going to store it. It's going to be inhibited if there is a scarcity of diet or you're fasting, or again, if you have physiological stress like infection, hypoxia, surgery, vigorous exercise, or you're in some kind of danger, right? This happens due to catecholamines like epinephrine and norepinephrine. And so, usually, in normal situations, glucose has a major control over the release of insulin. So, you consume glucose, it acts on your pancreas, and then you have insulin, and that eventually reduces the blood glucose. But in emergency situations, this control is completely replaced by the sympathetic nervous system. Now, the sympathetic nervous system is going to release something called catecholamines. Okay, catecholamines like norepinephrine and epinephrine, they have more of a control on the beta cells now, and this is going to cause a rapid mobilization of glucose from the liver. So where they were stored in the liver, right? They were stored in the liver because of the normal happenings, like the glucose was coming in, the insulin was releasing. But now you're in an emergency situation, and you need that glucose. So what the catecholamines are going to do is that they're going to cause this rapid mobilization and take the glucose from the liver and the fatty acids from the adipose tissue. Fatty acids from the adipose tissue, because sometimes the glucose is really less in the body and you really need glucose. And the first thing, I think we took this in the feed fast cycle, that the first thing that utilizes glucose is the brain in our body. So all of the glucose is going to go to the brain itself, and then the fatty acids are used for other parts of the body. That's why glucose from the liver and fatty acids from adipose tissue, in case there is a scarcity of glucose, right? Then you have carbohydrate metabolism. In the liver, it decreases the production of glucose through inhibition of glycogenolysis and gluconeogenesis. Glycogenolysis is basically breaking down of glycogen to give you more glucose, and you don't need that, right? And it inhibits gluconeogenesis, because why would you make more glycogen in the first place? Um, then in the liver and muscle, it increases glycogen synthesis. Um, the confusing part here is she said here that it increases glycogen synthesis, and here she said that there is no gluconeogenesis. The difference is that it's not increasing it from scratch itself. All right. In liver and muscle, it's not making it from scratch. It's just taking the already present ones and making the glycogen. All right, that's the difference. So in muscle and adipose, it increases glucose uptake by increase in GLUT4 transporters. So in the pancreas, in the previous ones, we took glucose comes in through GLUT2 transporters. In this one, in the periphery, you have GLUT4 receptors. Okay, let's go to the GLUT4 first. All right. What happens is that there's this insulin coming in, right? This is the periphery. These are your muscles and adipose tissues, and the insulin is coming in, and then goes to this receptor. All right, this is low-key a random receptor. When this receptor goes there, it starts forming this internal cascade. And because of that cascade, the GLUT4 receptors, they start coming up. So they come to the periphery, and more the glucose comes to the muscles and adipose tissues, more GLUT4 receptors start coming to the periphery, and then just keep taking in glucose and keep taking in glucose. That's basically the entire mechanism. And then they come back and they recycle back into the cell membrane. All right. Then you have the lipid metabolism. You have something called the hormone sensitive lipase. Uh, the thing is that last year, I think we took these lectures before the insulin and glucagon one, but you guys are taking the opposite. So that's not really good, honestly. But yeah, hormone sensitive lipase basically stops the degradation of fatty. Oh, 1 second. Why did that happen? Mm, okay. All right. 1 second. It causes the degradation. All right. Okay. So hormone sensitive lipase causes the degradation of fatty acids. So you don't want, again, as I said, you have these little particles, and these little particles need to come together, right? Because it's easier to store that way. That's what insulin does. So hormone sensitive lipase causes the degradation of fatty acids because we want storage, right? Um, so that's why we don't like hormone sensitive lipase. Insulin doesn't like hormone sensitive lipase. That's why it dephosphorylates it and deactivates it. Okay, the next one is TAG. I don't think she's gonna ask you much about hormone sensitive lipase and lipoprotein lipase, but just know whatever I'm saying. So I think you should be fine about that. She's gonna teach you the rest in the fat, fat metabolism lectures itself. Yeah, TAG increases the transport and metabolism glucose into adipocytes. So you have the fatty acids; they keep going into adipocytes, and then you have the glycerol 3 phosphate substrate, and then you increase the triacylglycerol synthesis. Like I said, you have fatty acids, then you need to increase the storage of them, then they come together and form TAGs. All right. This enzyme is also from the fat lecture. What it basically does is it increases the chylomicrons. Chylomicrons are it increases the degradation of chylomicrons. Chylomicrons are basically the dietary fats, and when the chylomicrons are degraded, they start being transported through something called, there's like HDLs, VLDLs, and stuff that you don't really need to know about right now, unfortunately know about later. But yeah, they need to be stored as TAGs again. So again, you're helping in the storing. So you need to increase this using insulin. Because again, insulin is used for storing and anabolism, right? Remember those two things. Now you have amino acid metabolism. So if you have an increased entry of amino acids into the cell, you're going to reduce this from the plasma because if you have amino acid in your blood and you're taking it into the cell, then eventually the plasma or the blood concentration of amino acid is going to decrease. You take it into the cell and then eventually you form proteins or the storage form again. So remember, you have to have the storage form and the fact that it's anabolic. I cannot write. All right. Okay, we went over this. Okay. You've probably seen this diagram like 10,000 times. This comes in my nightmares. Okay. You have insulin on one side and you have glucagon and epinephrine on one side. Insulin basically decreases glycogenolysis because why would you need to degrade the stored ones? You already have so much glucose going on in your body. It decreases gluconeogenesis. Neo basically means new, like you can, and lysis is basically breakdown, if anyone's confused. That's one way to remember it. Gluconeogenesis, why would you want to make new glucose? There's already glucose in your body and you're trying to store all of that. So that just does not make sense. You would decrease ketogenesis and you would decrease lipolysis because again, your fatty acids and everything is stored as TAGs, and you don't want to increase that fatty acid concentration in your blood. You want to store it. That's what insulin does. It stores and it's anabolic. Now, when we come to glucagon, it has a completely opposite effect because it hates insulin, right? It has uh, glycogenolysis. Now, you're gonna have low glucose, so it's gonna start depleting the sources like give all of it to me. And it's going to start making new ones, gluconeogenesis, and start making new. It's going to start making new ketone bodies, ketogenesis, lipolysis. Lipolysis because it's going to start depleting the fatty acid sources and then eventually give you more fatty acids. All right. Uh, Glucagon. Insulin was secreted by beta cells. Glucagon is secreted by alpha cells. Uh, Insulin does not have an A. In the spelling, glucagon has an A, so that's how I remember alpha cells. Secreted by alpha cells of the pancreatic islets of Langerhans, and this opposes the action of insulin along with catecholamines. This is what pro does to one. Catecholamines, cortisol, and growth hormones. All right. Okay, we're gonna go over this again, so don't worry. It activates gluconeogenesis and glycogenolysis. Okay. Again, you have the structure. And again, I don't think it's that important in MOL. I think she has better things to ask about. So it's a 29 amino acid chain. It's comparatively shorter to insulin, where you had 51 amino acids. The synthesis is similar to insulin, though. You have pre-pro hormones, like you had pre-pro insulin, then you have the pro hormone, then you have the main hormone, which is glucagon. Again, it has a shorter half-life, just like insulin did, and it's catabolic. Insulin was anabolic. Insulin just wanted to make storage of anything, all right? It was gatekeeping. Um, Glucagon is catabolic. Glucagon wants to break everything. And this is how it maintains the blood glucose levels by breaking everything. And liver is its primary target because all the storage and everything is in the liver itself. So it's going to go to the liver and break all the storage down. And that's then going to go into the plasma or the blood. Yeah. Okay, so the primary stimulus of glucagon release is a decrease in plasma glucose. So, for example, you're fasting and you did not take any food, right? This is going to increase, uh, no, this is going to decrease your blood sugar, right? This is going to decrease the glucose in your plasma, and you need like some sort of nutrients, right? You need some sort of nutrients. So your body has stored glucose from your previous meals, and now glucagon is going to go to the liver, as I said, primary target. Is going to go to the liver, and it's going to start breaking down these stores so that they can be released to the blood, and then this can like prevent your hypoglycemia. Hypo means less, glycemia is sugar, basically. Uh, then you have amino acids. Amino acids also stimulate release of glucagon. Uh, Basically, glucagon effectively prevents hypoglycemia that occurs after a protein meal. Why does this happen? Because if you had insulin, right, you have amino acids, right? You have amino acids, and you need to store these amino acids to transform them into protein. Remember, insulin is anabolic, so insulin is going to try and turn this whole thing into protein. So if you take a lot of amino acids, insulin is going to start acting up. It's going to be like, I want all of the amino acids, like nothing for the body. So the body is going to start going into like severe hypoglycemia, and then glucagon comes in, and glucagon prevents this, right? Is going to prevent this hypoglycemia that occurs after a protein meal. So amino acids mostly stimulate release of glucagon, because otherwise you're going to go into hypoglycemia, and that's not going to be very good. Yeah. Then you have catecholamines. Catecholamines, again, they stimulate glucagon by overriding alpha cells. Um, Before catecholamines, which again is norepinephrine and epinephrine, they went into beta cells. When they went into beta cells, they stopped insulin. When they stopped insulin, they increased the glucose, right? They went into the beta cells, stopped insulin, they increased glucose, and when they increase all the glucose is going to the muscles, and the muscles can use it effectively to run in emergency situations, basically in fight or flight situations, or when you're running away from labs. Yeah. Okay, so in catecholamines, in alpha cells, they're going to go there and they're going to increase glucagon. Because again, we need an increase in glucose, right? This can be done by reducing insulin or by increasing glucagon. All right? Glucagon. Because increased glucagon is going to increase your glucose, and then eventually you can use them in the fight or flight situations in the muscles itself. Okay. Again, this diagram is for glucagon. The previous one was for insulin. This is in alpha cells. You have amino acid. It increases glucagon because amino acids and insulin. Insulin is going to take all amino acids, and glucagon is going to fight the insulin and basically prevent hypoglycemia and everything. Epinephrine, as we discussed, epinephrine in alpha cells is going to increase glucagon, so you have increased glucose. And then when you have increased glucose, you can use them in the muscles effectively. Uh, Glucose or insulin, yeah, insulin is basically an op. We don't need it here. Then you have the metabolic effects of glucagon release. Okay. So when you have carbohydrates, you increase glycogenolysis and gluconeogenesis in the liver. All right. Okay. Then you have for fatty acids, you increase hepatic oxidation and formation of ketone bodies. And for amino acid, you increase uptake by liver, resulting in carbon skeleton for gluconeogenesis. So amino acids, you basically take them. All right. When you take them, you utilize basically their carbon skeleton, the CCCCCC thing, and you take those and you take the all the CCCCCC things and you form the glucose, right? That's how you use the amino acid. Fatty acids are hepatic. Okay, this is we went over this already. Okay, mechanism of action of glucagon. She didn't really go into detail for this, so I don't really know. I think the main thing you need to know is that adenylate cyclase, and this is the pathway. Because I think you learned all the pathways in ERP itself in the first physio lecture of ERP, that you have adenylate cyclase. So just remember that for glucagon you have adenylate cyclase and CAMP, and then you have all the cascade of enzyme reactions, which are all given here by the way, which we went through also. So yeah, the main things you need to remember is that adenylate cyclase and CAMP. Hmm, I repeated. Okay, so hypoglycemia. Uh, Hypoglycemia is basically when you have low glucose, all right? So your normal range is going to be up here, and then is going to start your hypoglycemia, right? Below 70. And then you're going to have severe hypoglycemia. At normal hypoglycemia, you're going to have really subtle neurological signs. Hunger, you have release of glucagon again. Why? Because glucagon is going to start increasing your glucose and try and balance out your hypoglycemia. Then you have epinephrine. Epinephrine has the same kind of the same function as glucagon. It goes against insulin, goes overrides the alpha cells, increases the production of glucagon, again increases your glucose. Then you have cortisol. Epinephrine is basically for short-term stress, and cortisol is for long-term stress. That's the only thing between them. And then you're gonna have sweating and trouble. Okay. But if you go in a state of like severe hypoglycemia, then you're gonna have lethargy, convulsions, and coma, because eventually, like you do need it for your brain, and your brain is gonna be the only one utilizing it. And at some point, your brain is also not gonna be able to use all the glucose because it's basically over, and eventually you're gonna have brain damage, and that's sad. When you have the types of hypoglycemia, you have the insulin-induced hypoglycemia. Um, Why does this happen is because again, if you have more insulin, your blood glucose basically goes down, and because of this you eventually have hypoglycemia. This next one is postprandial hypoglycemia. uh, I think you took this term in GIT itself. Postprandial. Postprandial means after a meal. So if you have like a big meal, so you have a big meal and an exaggerated insulin response, okay? So the insulin is basically going to decrease the whole glucose thing, and because of that, you're gonna eventually go into hypoglycemia. Like the thing I told you with amino acids, that's why glucagon comes into this and then saves you, right? Yeah. The fasting hypoglycemia. This is uh I wouldn't say the normal one, but I guess this most often happens because you don't eat enough, then you don't have enough glucose or anything. So you're eventually your glucose decreases in the peripheral tissues. Um, okay, so basically, if I were to say give you a summary, insulin-induced hypoglycemia, it also happens in diabetic patients. So because of insulin, you have a lot of insulin, your normal blood glucose is falling down. Postprandial, you eat and then your insulin increases, but it increases in an exaggerated level, which is why your blood glucose goes down. Fasting is just because you did not eat enough, so you don't have enough glucose. So again, hypoglycemia. Now, what happens in the response to hypoglycemia? You have pancreatic alpha cells which release glucagon, as we just took for the, I don't know, past 5 6 minutes. Then you have receptors in the hypothalamus. This is a new one, all right? And these two things, by the way, they overlap. Now, receptors in the hypothalamus trigger secretions of catecholamines and release of oh my god, adrenocorticotropic hormone or ACTH and growth hormone by anterior pituitary. And now these are gonna go ahead and have like eventually an effect, and that's gonna basically increase your glucose levels again. Right, this is basically showing you the hypothalamic regulatory center, pituitary, ACTH, adrenal gland. The ACTH acts on the adrenal gland, which releases epinephrine, cortisol, and whatnot. And all of that basically just increases your glucose again. All right. Uh, yeah, these are the two mechanisms that are like two overlapping mechanisms. I'm not writing that. Okay. You have glucagon and you have epinephrine. Again, glucagon and epinephrine are basically on the other side of the tug of war thing. Glucagon stimulates hepatic glycogenolysis and gluconeogenesis, right? Because it goes there and it depletes the store we have in case of emergencies like hypoglycemia, and it starts making new glucose because you need the new glucose. Epinephrine promotes glycogenolysis and lipolysis. There is no it does not make new glucose. It just starts breaking down what already is. So take it like if you're in an emergency situation, would you rather break down what you already have, or would you sit there and start making new things? Like you don't have enough food or anything to start making new stuff, right? That's why it's just gonna start breaking what it already has. So it's gonna start breaking down the glycogen stores, the lipid stores, because again, fatty acids in case you have a scarcity of glucose, because your brain needs glucose first, otherwise you're just gonna die. And epinephrine inhibits insulin secretion because why would you do opposite effects? Because insulin decreases glucose. Okay, so then epinephrine assumes a critical role in hypoglycemia when glucagon secretion is deficient. In stages of type 1 diabetes mellitus. So why is the T there? All right. We talked about type 2 diabetes mellitus. Sorry, type 2 diabetes first. Uh, Type 2 diabetes was in the sulfonylureas, right? In those ones, I said that type 1 diabetes is an autoimmune kind of diabetes. So your cells are destroyed, right? Over here, why we're using epinephrine instead of glucagon is because my pancreatic cells are destroyed. I cannot even make glucagon, right? So like obviously I'm gonna use whatever is next. And epinephrine is next. Epinephrine is the other hormone that helps me increase my glucose. That's why I'm using epinephrine, because I literally cannot make glucagon. My cells are destroyed. That's what happens in type 1 diabetes. Uh, type 2 diabetes, you still have your cells. So that's why in type 2 diabetes, we used the sulfonylureas, and that went and blocked the potassium channels in the cells itself because the cells are still alive, right? All right. This T is supposed to be here. Okay. The prevention or correction of hypoglycemia fails when the secretion of both glucagon and epinephrine is deficient. What is happening? All right. Basically, um, if both your glucagon and epinephrine is deficient, uh, nothing's gonna happen. You're basically gonna die, right? You have hypoglycemia because your insulin keeps increasing. Insulin has no opponent at all. It just keeps winning, and you go into hypoglycemia, coma, brain damage. You basically just die. All right. That's what happens. Um, okay. Glucagon, catecholamines, cortisol, and growth hormones are sometimes called the counterregulatory hormones because they counter the effect of insulin on glucose, right? Glucagon and epinephrine, as I just said, are the most important in the acute and short-term regulation, and cortisol is used in the long-term regulation. That's all you gotta know. The difference between epinephrine, glucagon, and cortisol. All right. How would you treat hypoglycemia? So in certain patients, you give them subcutaneous glucagon. So at the start, I'm giving this dude insulin, right? What is my insulin going to do? My insulin is going to start decreasing my blood glucose. When my blood glucose is decreased, I need it to increase back because I'm eventually going to die and I don't want that to happen. So I'm going to give them subcutaneous glucagon, and that's going to give me a huge rise. That's basically what she was saying. Um, okay. Uh, no, she didn't. I don't think she went over that much. This is basically what happens back to back in all of the hormones. If you have an increase in glucose, hold on. If you have an increase in glucose would increase your insulin, and if you're eventually when the insulin increases, your glucose decreases, and now you're going into hypoglycemia. And to prevent going into severe hypoglycemia or hypoglycemia at all, your glucagon is going to start increasing. But when your insulin is increasing, your glucagon is obviously decreasing because then there is no use of insulin at all. Again, this schematic diagram. Yeah, that's basically it. That was pretty small. And I hope that helped. Good luck for your TBL tomorrow. Um, yeah, thank you.